We now turn our attention to the directional nature of thermal radiation, and in that context we are going to define two terms, solid angle and radiation intensity. So, let us define these two terms, first solid angle and then intensity of radiation. Now, consider some area A2 which is drawn here, any arbitrary area, it may be flat, may be curved, does not matter, some area A2. We would like to find out the solid angle subtended by A2 at the point dA1. This is the area A2, let me write it in bigger letters, A2, all right, A2, and we would like to find out the solid angle subtended by A2 at dA1, at a differential area dA1. So, what we will do is the following: join the perimeter of A2 to the point dA1. So, you will get a cone as is being seen here, some kind of a cone will be obtained, all right. We will get a cone like this. Then with center at dA1, draw a sphere of unit radius, draw a sphere of unit radius with center at dA1. Now, the cone which we have drawn earlier will intersect this sphere of unit radius, and let us say that on the surface of this sphere of unit radius, the cone cuts out an area A. Let me repeat, let us say the cone cuts out an area A on the sphere of unit radius which we have drawn with center at dA1. The solid angle subtended by A2 at dA1 is numerically equal to A. Got it? The solid angle subtended by the area A2 at the point dA1 is numerically equal to the area A. So, let me now read out the definition which I have described to you. The definition of solid angle. Solid angle, we use the symbol omega for it and say construct a conical surface with vertex at dA1 passing through the perimeter of A2, what I said earlier. The solid angle subtended by the area A2 at the differential area dA1, that is at the point dA1, is numerically equal to the area A of the portion of the surface of a sphere of unit radius center at dA1 which is cut out by the conical surface. All right, this is the definition which I have described to you. And in 2 dimensions, the unit of an angle is radians. In 3 dimensions, the unit of an angle is steradian, SR, steradian. So, keep that in mind. All right. So, this is how we define the term solid angle. Now, let us take just to illustrate ideas, let us take the example of a, let us say, I take the example of a hemisphere. Take the example of a hemisphere. Consider a hemispherical surface A2 and a differential area, an elementary area dA1 at its center. Okay. Let me draw that. Suppose now I have a let us say this is a hemispherical surface and this is the hemispherical surface which I will call as A2, and the plane surface which is closing it, let us say the plane surface closing it at the bottom we will call as B, and at its center here let us say this is dA1, all right. So, A2 is a hemispherical bowl, dA1 is at the center of that hemispherical bowl. What is the solid angle subtended by A2 at dA1? Now, it is quite obvious that if I were to draw a sphere of unit radius with center at dA1, all right, then the area cut out on that sphere of unit radius is going to be 2 pi by the cone which is formed by joining the perimeter of A2 to dA1. Okay. Therefore, the solid angle subtended by A2 at dA1 will be equal to 2 pi. 2 pi will be the area cut out on the surface of a sphere of unit radius center at dA1. Got it? Now, let me change the example a little. I say suppose the area dA1 or the point dA1, instead of being located at the center, let us say it is located somewhere else on this plane surface B. Let us say this is dA1. Let us say this is dA1, all right. Now, I ask you the question, if this is dA1, what is the solid angle subtended by A2 at this red dA1? What is the solid angle subtended by A2, the hemispherical bowl A2 at this red differential point, differential area dA1 instead of being at the center? Okay. And you should be able to tell the answer yourself. Okay. Now, let us go on. We would next like to derive an expression for the solid angle subtended by a differential area dA. Suppose I have some differential area dA which I have shown here in spherical coordinates. Suppose I have some differential area dA which I am showing here in a spherical coordinate system here like this, all right. This is dA shown in a spherical coordinate system. I would like to know what is the solid angle subtended by dA in spherical coordinate system. Okay. Now, this is a typical spherical coordinate system. R is one coordinate, the radius r from the center to the area dA. Psi is the angle from the measured from the vertical, which is called the zenith angle, and psi, this is psi, and phi is the azimuth angle measured in a horizontal plane 0 to 2 pi, phi varies from 0 to 2 pi. Okay. So, the three coordinates in a spherical coordinate system are r, the radius vector, the radius, psi and phi, radius, zenith angle, azimuth angle. Now, the differential area dA is r squared sin psi d psi d phi, very easy to show by simple trigonometry. I will not show that to you. Okay. So, the differential area dA is r squared sin psi d psi d phi. Now, what is the solid angle subtended by dA at the center? It is very easy to see, it is nothing, it is going to be nothing but dA upon r squared, because r is the radius and we want the area cut out on a sphere of unit radius. So, dA upon r squared will be the solid angle subtended by dA at the center. Okay. So, d omega, that is the solid angle subtended by dA at the center, is equal to dA upon r squared, and we know that dA is r squared sin psi d psi d phi. Therefore, this is equal to sin psi d psi d phi. So, we have a nice simple expression for a differential solid angle in spherical coordinates. A differential solid angle d omega in spherical coordinates is equal to sin psi d psi d phi, where psi is the zenith angle and phi is the azimuth angle, and we will use this shortly. Now, let us define the second term which I mentioned. What was the second term which I mentioned just a few minutes ago? The second term which I mentioned was intensity of radiation, radiation intensity or intensity of radiation. To be more specific, we will call it total intensity of radiation. Total means summed over all wavelengths, the usual definition. Total means summed over all wavelengths. The total intensity of radiation in a given direction I is equal to the radiant flux passing in the specified direction per unit solid angle. Radiant flux passing in the specified direction per unit solid angle. What we mean is the following. Suppose I have a surface, all right, like this, and it is emitting radiation in all directions like this. In normal direction, at an angle, all directions given by a hemisphere, emitting radiation in all directions given by a hemisphere. If I am taking any element on the surface, that element is emitting radiation in all directions of a hemisphere. Okay. I want the intensity in a particular direction. So, I say to myself, suppose I have some direction, some specific direction like this, which I will draw in red. I want the intensity in this direction. So, in this direction, about this direction in which I am interested, let us draw a small elementary solid angle d omega like this. All right. Let us say this is an elementary solid angle d omega, and let us say through this elementary solid angle d omega, the radiation which is being emitted from this surface is d E. Okay. Therefore, I is nothing but d E d omega, the radiant flux emitted per unit solid angle in a particular direction, d E upon d omega. Or another way of looking at intensity of radiation is to say it is that quantity which, when integrated over all directions of a hemisphere, will give me the emissive power of a surface. So, let us put it in the reverse way here. Therefore, E is nothing but the integral I d omega, where the integration is carried out over all directions encompassed by a hemisphere. So, there are two ways of looking at I. One is it is the radiant flux, so many watts per meter squared per unit solid angle in a given direction, or it is that quantity I is that quantity which, when integrated over all directions encompassed by a hemisphere, will give me the emissive power of a surface. All right. And the word total implies that we are talking about something which is summed over all wavelengths. Intensity means you have to sum it over all directions to get the emissive power. Thus, proceeding from the earlier expression, for E is equal to integral I d omega. Now, instead of d omega, I will write sin psi d psi d phi, because that is my expression for the elementary solid angle. I have derived it earlier in spherical coordinates, and if I want all directions of a hemisphere, integrate from 0 to pi by 2 to cover all the variation of the zenith angle, and from 0 to 2 pi to get the variation of the azimuth angle. You follow? Both these 0 to pi by 2 covers the vertical in the from the zenith vertical direction down to the horizontal plane, and 0 to 2 pi covers the azimuth angle in a horizontal plane. So, all the directions of a hemisphere are covered when I do this integration. So, I say E is equal to the double integral 0 to 2 pi 0 to pi by 2 I sin psi d psi d phi. That is our one way also of looking at the relation between E and I. E is the emissive power, I is the intensity of radiation. Now, it so happens that for many surfaces, the intensity of radiation in any direction can be related to the intensity in the normal direction by a simple law which is called as Lambert's law. And Lambert's law simply says I is equal to I n cosine of psi. What we are saying in effect is the following: if I have a surface and if this is the normal direction to the surface, the intensity in the normal direction is I n, the intensity in any direction other direction is I, okay. And let us say that direction makes an angle, zenith angle psi with the normal. Then what we are saying is Lambert's law simply says I, the intensity in any direction, is equal to I n, the intensity in the normal direction, multiplied by the cosine of psi. Such a surface, which is defined by Lambert's law, which relates intensity in any direction to intensity in the normal direction, such a surface which says that Lambert's law is valid, is called a diffuse surface. Okay. So, we say, and many real surfaces to a large extent obey this law. Therefore, we will use it often as an idealization. Now, suppose we substitute Lambert's law into the expression which we had earlier. E is equal to integral 0 to 2 pi 0 to pi by 2 I sin psi d psi d phi. Instead of I, let us write I n into the I n into the cosine of psi. I think we have forgotten something here. We should have had I n into cosine of psi. I have forgotten that here. I n into cosine of psi into sine of psi into d psi d phi. Okay. Now, that is correct. If you perform this integration, take the I n outside and perform the double integral over psi and phi, it is very easy to show that you will get pi. So, the net result of the integration is simply to say E is equal to pi times I n. So, we have got a nice easy relationship, simple relationship between the emissive power of a surface and the intensity in the normal direction. So, let me repeat. First, we had a general expression for E. E is equal to the double integral I sin psi d psi d phi. It is a general expression. Lambert's law relates the intensity in any direction to the normal intensity. Substituting Lambert's law, that is assuming that the surface is diffuse and performing the integration, we get E is equal to pi times I n. That means, we are saying the intensity in the normal direction multiplied by pi is equal to the emissive power of a surface if the surface is diffuse. E is equal to pi times I n if the surface is diffuse, and we will make this assumption. It is made by most people, we will make this assumption. So, we will always relate the emissive power to the normal intensity by this expression, assuming Lambert's law to be valid. Okay. So, now let us do a simple problem again, just to illustrate ideas. Let us do the following problem. Okay. Let us say, let us do the following problem. Let us say I have a surface, some surface at a surface at a temperature of 800 Kelvin. Okay. Take some element on that surface, some elementary area on the surface, and we know that it is going to be emitting radiation in all directions of a hemisphere. Like this. it's emitting radiation in all directions of a hemisphere. Now, let us assume the surface emits, surface emits radiation in a diffuse manner, or assume surface is diffuse, okay. And let us say that the emissivity of the surface is 0.08. So, surface is 800 K with an emissivity of 0.08, it emits in a diffuse manner. Calculate. First of all, calculate the value of I n, the intensity in the normal direction. B, radiant flux emitted within the cone within the cone 0 less than psi less than 50 degrees, 0 less than phi less than 2 pi. Okay. So, we would like to know how much radiation is being, how much radiant flux is being emitted within the cone, which has a semi angle of 50 degrees. So, let me draw that. Let us say this is 50 degrees here. This is the 50 degree cone. All right. So, this is 50 degrees. Within this cone, how much is the radiant flux going outwards? That is what we would like to know. Not all of it, but what is going out within the cone. If you want the whole amount that is going over the whole hemisphere, that is obviously nothing but the emissive power of the surface. We do not want that. We want only the amount that is within this cone, making an angle of semi angle of 50 degrees. So, let us do the problem. First of all, from the Stefan-Boltzmann law, SB law, E is equal to epsilon times E b is equal to 0.08, that is the emissivity, multiplied by 5.670 10 to the minus 8 multiplied by 800, that is degrees Kelvin to the power of 4. So, that comes out to be 1857.9 so many watts per meter squared. We want first of all the value of I n. We know very well that if it is a diffuse surface, a surface which emits in a diffuse manner, I n is nothing but E divided by pi. So, that comes out to be 591.4 so many watts per meter squared steradian. So, that is I n, that is the first thing that we are looking for, the value of I n. The second thing we are looking for is the radiant flux being emitted in the cone 0 to 0 less than equal to psi less than equal to 50. So, radiant flux in cone 0 less than psi less than 50 is equal to the double integral 0 to 2 pi, that is integrating over the whole azimuth angle, 0 to 50, that is the zenith angle, I n cosine psi sin psi d psi d phi, all right. So, now note earlier when we had integrated over the whole hemisphere. So, we had 0 to pi by 2 and 0 to 2 pi. Now, I want the radiant flux only in this cone. So, the first the integral over psi is only from 0 to 50, the integral over azimuth angle is over the whole direction encompassing a whole horizontal plane, going over the whole horizontal plane. Now, this is an extremely trivial integral to do. All that we will get is this is equal to 2 pi I n, the integral 0 to 50 sin 2 psi by 2 d psi, and that comes out to be 1090.3 watts per meter squared. That is the second answer we are looking for. That is the radiant flux emitted within the cone, which has a semi angle of 50 degrees. All right. So, this is an illustration of the formula that we have just derived for intensity of radiation and for solid angle. Okay. Now, let us move on. We have defined two terms, solid angle and radiation intensity, and in the process also defined what we mean by a diffuse surface, saying that it relates intensity in any direction to the intensity in the normal direction. Now, we go on to another law which we are not going to prove, but which is in fact a very important law, and that law is Kirchhoff's law. Kirchhoff's law states that the monochromatic emissivity of a surface is equal to its monochromatic absorptivity if the surface emits in a diffuse manner. Kirchhoff's law is a very powerful statement relating the emission characteristics of a surface with the absorption characteristics of surface. Kirchhoff's law, I repeat, is a very important law, relates emission characteristics to absorption characteristics of a surface, and it states if the surface is diffuse, epsilon lambda is equal to alpha lambda. If a surface emits in a diffuse manner, epsilon lambda is equal to alpha lambda. This is, we are not going to prove this law, but I will ask you to take it as correct. Now, a consequence of this is that if in addition to being emitting in a diffuse manner, if I say if the surface is also gray, it follows that epsilon is equal to alpha, emissivity is equal to absorptivity, and this is quite easy to show. If epsilon lambda is equal to alpha lambda and the surface is gray, then epsilon becomes equal to alpha. Now, let us show that. It is quite relatively easy to show. Let us for instance say take epsilon. Let us take the quantity epsilon, that is the emissivity of surface. What is epsilon equal to? Epsilon is E upon E b, that is E is the emissive power of the surface, E b is the emissive power of a black surface at the same temperature. E is nothing but the integral 0 to infinity E lambda d lambda, integration over all wavelengths upon E b, that is nothing but the integral 0 to infinity epsilon lambda E b lambda d lambda upon E b. All right. Now, epsilon lambda is a constant. Epsilon lambda is a constant. We are told that epsilon lambda is a constant. Okay. Therefore, this is nothing but, I can take epsilon lambda outside the integral, epsilon lambda 0 to infinity E b lambda d lambda upon E b, that is nothing but epsilon lambda E b upon E b, and that is nothing but epsilon lambda. You understand? So, the emissivity is equal to the monochromatic emissivity the moment I assume that the surface is gray. Similarly, the alpha it can be shown that alpha, the absorptivity, is equal to the also equal to epsilon lambda if the surface is gray and diffuse. All right. Therefore, epsilon is equal to alpha. I am not showing the second thing, that alpha is equal to epsilon lambda, but you can show it in the same way that we showed earlier for epsilon. Say alpha is equal to h a upon h, then go ahead and make h a, describe it in terms of an integral and use the fact that alpha lambda is epsilon lambda, which Kirchhoff's law states, and you can show alpha is nothing but epsilon lambda. So, therefore, in effect we are saying, let me repeat again, Kirchhoff's law states epsilon lambda is equal to alpha lambda if the surface emits in a diffuse manner. All right. In addition, if the surface is gray, then it can be shown that epsilon is equal to alpha, and that is a very powerful statement. We will generally make the assumption that the surface is diffuse and gray. A real surface that we are dealing with is diffuse and gray. Okay. So, a surface for which both the equations, that is epsilon lambda is equal to alpha lambda and epsilon equal to alpha, a surface for which both the equations hold is called a diffuse gray surface. We will assume that all real surfaces, all non-black surfaces that we are dealing with are diffuse gray. We will make that assumption. All right. And therefore, we will always assume epsilon equal to alpha and epsilon lambda equal to alpha lambda. It is a powerful law which will help us quite a lot in deriving formulae and simplifying our derivations as we go along. All right. Now, we have so far, let me again recapitulate for a moment. We have talked about the emission characteristics of surfaces and defined terms like emissive power, emissivity, monochromatic emissive power and monochromatic emissivity. And we have defined the laws of black body radiation, emissions from black bodies. Secondly, we have talked about the absorption characteristics of surfaces, defined quantities like absorptivity, monochromatic absorptivity, and similarly analogous quantities for reflectivity and transmissivity. All right. Then we have looked at the directional aspect of radiation today, defined quantities like solid angle and intensity of radiation, that is radiation in a particular direction. We have related intensity in the normal direction to the emissive power of a surface by making the assumption that Lambert's law holds true, that is the surface emits in a diffuse manner, I is equal to I n cosine of psi. Finally, we have stated Kirchhoff's law, which states that the monochromatic emissivity of a surface is equal to the monochromatic absorptivity if the surface emits in a diffuse manner. We have gone on to show that if in addition the surface is gray, then emissivity is equal to absorptivity. So, now that we know how to deal with emissions from a surface and the absorption characteristics of surface, we are ready to talk about heat exchange by radiation between two surfaces at two different temperatures. Now, we are ready because a surface emits, a surface absorbs. All right. So, we are now in a position to calculate heat transfer by radiation between two surfaces. So, let us do that now. We are going to study the heat transfer by radiation between two surface elements. So, to simplify matters, first instead of taking finite surfaces, we will take two surface elements, and to also simplify matters, we will assume that they are black. That is our initial assumption, mind you. Later on we will be able to deal with other situations. So, first now let us calculate the heat transfer by radiation between two black surface elements. Let us say the black surface elements are dA1, this is one black surface element, and dA2. There are two black surface elements, two surface elements arbitrarily located somewhere in space. Okay. dA1 is at a temperature T1, an absolute temperature T1, and dA2 is at an absolute temperature T2. It is maintained, both of them are maintained at these absolute temperatures T1 and T2. So, obviously, dA1 is going to emit radiation by virtue of being at T1, dA2 is going to emit radiation by virtue of being at T2. Some of the radiation emitted by dA1 is going to go towards dA2, and similarly, some of the radiation emitted by dA2 is going to go towards dA1. That radiation is going to be absorbed by dA2 and dA1. All right. The heat transfer by radiation between the two elements is the difference between those two quantities, that is, what is emitted by dA1 going towards dA2 and absorbed by dA2, and what is emitted by dA2 going towards dA1 and absorbed by dA1. So, to calculate the net radiative heat exchange between dA1 and dA2, that is our problem. All right. Now, let us do that. Let us solve, get an expression. First of all, let me consider the radiation emitted by dA1 and going towards dA2. So, I ask myself first, what is the intensity of radiation I emitted by dA1 in the direction of dA2. What is the intensity of radiation? Now, let us go back to the sketch for a moment, define some symbols before we put down this expression. Let me show the sketch again. These were the areas dA1 and dA2 at temperatures T1 and T2. Let us say the line joining these two areas, this is a line joining these two differential areas, and let us say its length is L, is denoted by capital L, and that the normal to dA1, makes an angle beta 1 with L, the normal to dA2 makes an angle beta 2 with L. All right. So, beta 1 and beta 2 are the angles made by the normals to dA1 and dA2 with the line joining dA1 and dA2. That is the nomenclature we will adopt. Okay. Now, let us go back. With this nomenclature, intensity of radiation I emitted by dA1 in the direction of dA2 is going to be equal to, first of all, what is the emissive power of dA1? The emissive power of dA1, it is a black surface. So, by the Stefan-Boltzmann law, it is sigma T1 to the power of 4 EB 1. If I divide this by pi, I have got the intensity of radiation emitted by dA1 in the normal direction. I want the intensity emitted by dA1 in the direction of dA2. So, I will use Lambert's law and say multiply by cosine beta 1, that is the intensity in the direction of dA2. Got it? All right. Next, what is the solid angle? D omega subtended by dA2 at dA1, it is nothing but, first of all, take the area normal to the line joining the two, that is normal to L, area of dA2, projected area of dA2 normal to L it is going to be dA2 cosine beta 2, all right. That is the area of dA2 normal to L. I want the solid angle. So, obviously, I want to know how much will be cut out on a sphere of unit radius. The area of a sphere is 4 pi r squared. So, if I divide this by L squared, then I get the area cut out on a sphere of unit radius. So, this is d omega. Okay. Therefore, I know the intensity of radiation emitted by dA1 in the direction of dA2. I know the solid angle subtended by dA2 at dA1. Therefore, rate at which radiation emitted by dA1 flows towards dA2 that will be nothing but is equal to I, the intensity, multiplied by d omega multiplied by the area dA1. I is sigma T1 to the power of 4 upon pi cosine of beta 1, that is I. D omega is dA2 cosine of beta 2 upon L squared, and finally multiplied by dA1. That is the expression for the rate at which radiation emitted by dA1 flows towards dA2. Rate at which radiation emitted by dA1 flows towards dA2 is given by this expression. Let us clean it up a little. I can rewrite that as same expression. I can say that is equal to cosine beta 1 cosine beta 2 dA2 divided by pi L squared, the whole thing multiplied by sigma T1 to the power of 4 dA1. I have just rewritten the same expression in another manner. And I am going to the quantity within the curved brackets, I am going to indicate by the symbol dF 1 to 2 and say that is equal to dF 1 to 2 sigma T1 to the power of 4 dA1. Okay, that is the rate at which radiation emitted by dA1 flows towards dA2. And all this is absorbed by dA2, all this is absorbed by dA2. Why is that? Because dA2 is a black surface absorbs. So, this is the expression where, let me indicate, the symbol dF 1 to 2 is equal to cosine beta 1 cosine beta 2 dA2, all right, divided by pi L squared. That is the quantity dF which we have defined as dF 1 to 2. dF 1 to 2 is called the shape factor of dA1 with respect to dA2. dF 1 to 2 is called the shape factor of dA1 with respect to dA2. It is also referred to as the shape factor. Let me underline that word. This is called the shape factor also referred to as the view factor, referred to as view factor. It is sometimes called as an angle factor, sometimes called as a configuration factor. The shape factor is also referred to as a view factor, angle factor or a configuration factor. Okay. Now, what does it mean really? That is important. The shape factor, if you go back to the definition here, is the fraction of the radiant heat flow rate from dA1 which is intercepted by dA2. The shape factor is going to be a number between 0 and 1. It stands for that fraction of the radiant heat flow rate emitted from dA1 which is intercepted by dA2. Okay. So, dA1 is like this, some elementary area emitting in all directions, dA2 is somewhere here. So, a certain amount of that emitted radiation goes towards dA2. The fraction out of the total amount that is emitted over a whole hemisphere, which goes from dA1 towards dA2, is called the shape factor of dA1 with respect to dA2. So, it is always a number between 0 and 1. That is the physical meaning and you must never lose sight of that. All right. So, now that we have this, let us go on. We have not yet got the final expression. We know what is the radiation emitted by dA1 which is flows towards dA2 and is absorbed by dA2, so many watts. Similarly, let us do the reverse calculation now. Similarly, rate at which radiation emitted by dA2 flows towards dA1 and is absorbed by dA1, because dA1 is black, and is absorbed by dA1. Similarly, it can be shown this is equal to sigma by pi cosine beta 1 cosine beta 2 dA1 dA2 divided by L squared into T2 to the power of 4, which we can write as dF 2 to 1, again define a shape factor, into sigma into T2 to the power of 4 into dA2. Note again shape factor dF 2 to 1, where dF 2 to 1 is equal to cosine beta 1 cosine beta 2 dA1 divided by pi L squared divided by pi L squared. That is the shape factor dF 2 to 1. Okay. So, you got two expressions, rate at which radiation emitted by dA1 flows towards dA2 and is absorbed by dA1. We have a second expression, rate at which radiation emitted by dA2 flows towards dA1 and is absorbed by dA1. Therefore, the net radiative exchange rate, which we will call as dQ 1 to 2, between dA1 and dA2. This is what we are looking to calculate. The net radiative heat exchange rate dQ1 to 2 between dA1 and dA2 is equal to rate at which radiation emitted by dA1 is absorbed by dA2 minus rate at which radiation emitted by dA2 is absorbed by dA1. Okay. So, that is equal to, putting both the expressions in, sigma by pi cosine beta 1 cosine beta 2 dA1 dA2 upon L squared into T1 to the power of 4 minus T2 to the power of 4, all right, which is equal to, if I want to use the first shape factor dF1 to 2, it is equal to dF1 to 2 sigma T1 to the power of 4 minus T2 to the power of 4 into dA1, or using the second shape factor dF2 to 1 sigma T1 to the power of 4 minus T2 to the power of 4 dA2, all right. So, all these are equivalent expressions which we have put down for the net radiative heat exchange rate between dA1 and dA2. And mind you, again I keep the physical meaning of shape factor in mind, that is important. dF1 to 2 stands for the fraction of radiation emitted from dA1 which goes towards dA2 and is absorbed by dA2 in this case, because dA2 is black. dF2 to 1 similarly is the fraction of the radiation emitted from 2 which goes towards dA1. So, note from the definition that dF1 to 2 dA1 is equal to dF2 to 1 dA2, keep that in mind. So, we have now, based on our knowledge of emission characteristics of a surface and our knowledge of intensity of radiation, that is radiation going in a particular direction, today we have derived an expression for the net radiative heat exchange rate dQ1 to 2 between two arbitrarily oriented differential areas dA1 and dA2 at two different temperatures T1 and T2, all right. We know what is the net radiative heat exchange rate between them by calculating what is emitted by one and absorbed by the other, what is emitted by 2 and absorbed by 1. That is what we have got. In the process, we have defined a very important term called the shape factor, which is the fraction of the radiation emitted by one surface which flows to the direction of the other surface.